Hey guys. So today we're going to talk about triple integrals, and as it turns out, these are pretty chill. There's some stuff here, but the difficulties are mostly related to like thinking about geometry and not really related to the concept being hella new. So here's the like basic idea that I want you to recall from like I don't know Calc 1 or something, right? Um, in Calc 1, we do this thing where we like want to find the area under a curve. So we like say, all right, here's a value A I want to start at, here's a value B I want to end at. I make a whole ton of these little rectangle Madus. And then I go, oh, this little rectangle Madu right here is like, let's see, the area of that is like approximated by like something about how high it is. So we like take a particular point in that interval, like down here at the base, right? Like pick a special point down there. Could be the left hand side, could be the right hand side, could be the midpoint, could be some other point, right? Anyway, I pick a point in the kind of bottom, and then I say, okay, the height of above that point is I take the function value at that point, and then I might multiply here by something like delta x, right? Um, and then I'd like add all these up. That'd give me the like total area under the curve, right? Same deal. We've done this a couple of times. We were just doing volumes under curve or under surfaces a minute ago. So I'm hoping that that's fresh in your head. Here we're going to do basically the same thing, but with three pieces. So I'm going to take a region in space and I'm going to chunk it up into little cubies. So here is my artist representation of a little cubie. Cubie. Okay, and in my kind of representation here, I'm going to have a delta x on this side, I'm going to have a delta y on that side, and a delta z on this side. So I've got a width, a length, and a height, right? Now, if I wanted to know the volume of this little box, I'd just multiply those three things together, right? So I might write something like a little volume box is basically an x change times a y change times a z change, right? This is going to be something we do a fair bit. In order to kind of motivate triple integration, though, I need a question. So my question is something like, what's the total mass of an object? So I have here on my desk an object. This happens to be a GoPro. If I wanted to calculate the total mass of this object, I could say something like, okay, the back part is a screen. And so it's basically glass, right? In the middle, there's a bunch of electronic components. And then at the front, there's another little chunk of glass. Along the sides, there's like plastic coating to keep things safe, right? So I might say, okay, I could write down a density function, right, that would take a coordinate in the GoPro and tell me how much does a little tiny bit right there weigh, right? We can envision having density functions for lots of things. One of the cool applications of this is you might figure out the total mass of, I don't know, a planetoid or something using this. In fact, that gets kind of relevant to astrophysics. So when you think you know how a planet's made, you might like check to see if your supposition about how the planet's made actually adds up to the right mass. So one of our kind of primary applications is going to be integrating over a region. I'm going to put an omega here, but you could put an r. Yeah, what the heck? Let's put an r here. So we're going to integrate over a region, some density function of x, y, and z, d volume. Doesn't have to be a density function, so I'm going to swap that out for an arbitrary f. But I want you to think about f as oftentimes being a density function. It doesn't necessarily have to be the density of matter in there. Could be the density of mosquitoes in a space. Could be the density of energy in the space, right? We could integrate the temperature function to figure out the total energy in a space. We've got lots of options for this. Our usual doing of this is if we have a rectangle here, so a region R that is truly a rectangle, might be A, B by C, D by, I don't know, R and S or something. So that's a region where the X's are in the interval from A to B, the Y's are in the interval from C to D, and the Z's are in the interval from R to S, right? I have a convenient picture here of such a region. I made this thing so you can play with the variable sliders, right? So we can make it wider. You'll notice some artifacting here. That's actually just artifacting. It's not supposed to be doing that. So we can make it kind of wider or narrower. Right? We're kind of moving it around. We can make it kind of squish it in the y direction, or we can make it wider in the y direction. Right? As we move this thing around, we might get kind of different answers for this, right? You can see here I've got my little grid, right? And if I chunked up the sides too, I'd have this chunked up shape, right? And then I'd need to go through and add up all the little boxes. So in terms of actually doing this, the way we're going to do it is we're going to say, okay, I'm going to pick an ordering of my X, Y, and Z variables that makes sense for me. In the case that you have a rectangle, I would go ahead and pick them in the laziest possible order, X, Y, and Z. Then this first integral is going from A to B because that's associated to X. So that's these bounds here go with this variable here. The Y bounds are going to go from C to D. That's going to be my second set, right? The middle set. So that's middle set goes with Y. Oops, where'd my green underline for X go? And then my last set is going to be from R to S. And those are going to be my Z bounds, right? And then otherwise, we're just going to integrate this the exact same way we just did two-dimensional stuff. You're just going to go ahead and do it. Now, there gets to be a little bit of excitement, say, when we're doing a more general region. So that's going to be our triple integrate over a more general region. So when we're triple integrating over a more general region, let me go get a more general region here for you. Oops, not that one. Here's a more general region. So this is a region in space. It's bounded between a let me turn some of this stuff off. So the bottom of it is just the paraboloid z equals x squared plus y squared. The top of it is the hyperbolic paraboloid z equals x squared minus y squared plus 3, right? That's just our usual saddle shifted up 3 units. And we're talking about the region in between these two shapes. So I've added this thing. You guys might imagine a world in which you needed to find, like, say, the volume of this or like the mass of it given certain densities. These problems arise in mechanical engineering all the time, where you have to make a part. You want to know how much is it going to cost to make this part? How much is it going to cost? Depends a lot on how much of it there is, right? So when we're first kind of going about this, we might want to figure out something like, say, actually, what the hell? Let me type this. What's the volume of the region above z is x squared plus y squared, and below z is x squared minus y squared plus 3. There's one more kind of thing here I need. So I'm going to say inside x squared plus y squared equals 1. And I'm going to bring that shape back. Okay, so here's my little shape. I want you to think about, why did I need that last statement about inside x squared plus y squared is 1. You see that? Because I cut this thing off with a cylinder, right? That's actually what this parametric surface here is, right? It's the skin of a cylinder that I use to plunge this thing out, right? So in my case, I've got kind of 3 things playing here. And we just need to figure out a way to find the volume of this region. So I'm going to start by saying, actually, I'm going to keep this guy. Let me snip this little dude out so I can draw on it a little bit. Okay, so here's my little dude. And I'm interested in what's the volume of this region. So the first thing I'm going to do is I'm going to go inside of it to an arbitrary point, and I'm going to say, all right, if I'm inside here, so that's going to be a point on the bottom paraboloid, and I'm going to just kind of trace that up here till it hits the top, right? So that there represents, I picked a random point, and I want to know about the change in height of this thing, right? So I'm thinking to myself, okay, I'm going to do some integrating, right? And the volume function, or the density of volume, is 1. So I'm going to put a 1 here. And then I'm going to put a D, and a D. And I'm trying to figure out the bounds for my region here. So in my case, I'm going to say, it looks to me like Z is going to be the easy one to figure out, right? If I think about all the little rectangles in here, if I put them from side to side, right? If I went like in this blue direction from, oh, that's going to be impossible to see. If I went in a green direction across the inside of the shape, right? Like in the Y direction first, I'd have, sometimes it just hit the sides. Sometimes it would hit the hyperboloid, the hyperbolic paraboloid on the top, on both sides, and other times it would hit the regular paraboloid on both sides of the bottom. That kind of generally sucks, because that means I'm going to have to split this integral into a bunch of pieces. So I'm not going to do that. If I did it with respect to x first, I'd run into the same problem. I'm going to do it with respect to z first, because I'm going to be able to say, look, man, the z's, they range from the bottom shape to the top shape, and that's all there is. So the z bounds here, I'm going to color in red, are going to go from the bottom shape, so that's x squared plus y squared, to the top shape, that's x squared minus y squared plus 3. Easy peasy. I know this is not actually easy. This is kind of hard. So here's the like word to the wise. Once you've done this part, which is the new part, then you're actually in one of these 2-dimensional problems that you've done before. So after smashing, right, z-wise, so I'm just taking that shape and I'm going like, boom, no more z's. I get this shape here. This circle, when a is 0, is x squared plus y squared is smaller than 1, right? So I'm looking at this shape. Now, that means that I'm going to be able to integrate either x or y out. So I'm going to take this thing and I'm going to go for the y's. The y's go from minus the square root of 1 minus x squared to plus the square root of 1 minus x squared. And I know, you're shouting, dude, use polar, don't be dumb. You get what you pay for. And because I'm not going to actually do this integral, I'm much more comfortable doing this. So which variable needs to go here? I want you to think about this. Good. Y's. Now, the reason that my little shape there had such dorky little numbers in it is I wanted to make this animation. So now that we've integrated the y's out, we can smush. Okay, and now we need to worry about our x values. And our x values, last of all, are going to go from -1 to 1. Now, you don't have to do it this way. You could do polar. If you do polar, you'll have to convert these x's and y's too. It's not a bad idea. Actually, a pretty darn good one. Another thing you can do is you can say, all right, look, Joe, I'm actually going to integrate over this circle of radius 1 after I get done with this. So now I'm going to integrate here, x squared plus y squared. I use this trick fairly often. You'll catch me using it in class. This is me just wanting to short circuit. I don't really want to switch to polar until I've integrated, and then maybe I can reduce a little bit. Might make the switch to polar a little easier. You do you. If I do this, I'm going to write dz d area here. I think this double integral is a little bit ambiguous. I'm thinking about those as being one symbol stuck together. So it is what it is. You guys can do this. I promise this isn't actually harder than double integration. It just has one more step. The big thing is going to be getting the shapes right. And for the shapes, the thing you need to think about is which direction should I start with? You don't always start with Z. You guys can do it in any order you want. Sometimes the other orders make a lot of sense. So if you choose to do from Y to Y first, then you'll smash it onto the XZ plane, right? And then, sorry, Y to Y, I guess it's this way. You'll smash it onto the XZ plane, and then you'll have another region, and then you'll have another two-dimensional problem to do. If you choose to smash it in the X direction, right, you integrate dx first, then you should have some integral dy dz. That's a region in the YZ plane that you can deal with. So short video, hopefully chill. Hit me up when you get stuck. Mostly it's going to be drawing the shapes.